In this lesson, we're going to be talking about how to find the area between two functions. And visually, this looks very, very challenging, but fortunately, mechanically, this is actually a very easy thing for us to do. With a simple twist of what we already know, the number of applications that we can now attack are huge. And so this is a really nice bonus for us. So in order for us to sort of grasp all the different sort of twists and turns, I wanted to go back to sort of the beginning of what finding the area underneath one curve looks like. So if I were to challenge you to find the area that is created by the sine function and the x-axis between 0 and pi, it would be this area here. And all we would do is we would simply integrate sine. We'd have a definite integral of sine, and we would evaluate it from 0 to pi. And we should find that that result is 2. All right, and if we were to translate the sine function, let's say we subtract 0.5 or a half from our sine function, where part of our curve is below the x-axis and part of it is above, and so we have this alternating situation here. And we were to then find the definite integral of this function from 0 to pi, the answer would be 0.43-ish, and that's because the area that's below the x-axis would come out as being negative, and the area above is positive and negative. And so the net result, the net area, is going to be this area above minus the area below, and which we consider negative. And so the net result is this difference here, 0.43. Now later on in some applications, we're going to want to consider all these areas positive and add them all together as total distance, and we'll talk about how to do that in another lesson. But for right now, if I were to just take the straight definite integral of this function from 0 to pi, it would give the area above and subtract the area below. So keeping this in mind, what I'm going to do is challenge us to think about what would happen if I wanted to find the area not between my curve sine x and the x-axis, but between the sine function and some other function. And let's take a look at what that would actually look like. So what I'm going to do is I'm going to change my sine function. I'm going to add, I'm going to make it sine x plus 2. So now we have this area here. I'm going to introduce a new function here. I've hidden it. It's over here. I'll go ahead and show this new function. So I have the sine, this function 0.5x, this linear function. And what I want to do is I want to find the area underneath the sine function, but above this line. And what I would do to do that is I would find the area under my sine function, which is here in red. I would find the area underneath my linear function here, which is in blue, which kind of looks purple here because it's on top of the red. And I would subtract them. By subtracting these two areas, I get this area right up in here. And that is a very simple application. So if I take these two areas, I subtract them, I get the area between the two curves. And so simply by subtracting or finding the difference between the two integrals, I can find the area between two curves. And so that's the how we evaluate the area between two functions. So one more time, if I have an upper function f, a lower function g, and I wanted to find this area, this shaded area between these two curves and between a and b, these two boundaries, what I would do is I would find the area of the upper curve and I would subtract the area of the lower curve, and that would give me my overall area right here. So algebraically it looks like this. So I would simply find the difference between the two functions. That's a fantastically easy way of doing it. Now, some of the issues that we may run against is like, what if some of the curve is above the axis and some of the curve is below the x-axis, and actually the integral just takes care of that for you. So for example here, we have this function here, that's the upper curve, and this lower curve, but this lower curve dips below the x-axis. So what's going to happen if we subtract, if we want to find the area of these two? Do we have to do something kind of strange or funky? And the answer is no. We could just do f of x minus g of x from a to b, and what it would give us is it would give us this total area. It wouldn't subtract this area down below. And why is that? Well, the area down here, the difference between these two functions is going to compensate for this area down below here. And so let me try to describe that in a different way. So over here, another way to think about the area between two curves is really we found the area underneath the curve by adding up a bunch of different rectangles. And so previously our rectangles had a width, a change in our x value, and then what we would do is we would multiply it times our height, which is the value of our function at that point. So what we're doing now is we're doing the same thing. We have rectangles with a small thin change in x, and then the height of the rectangle is actually the difference between the two functions, f of x and g of x. And it doesn't matter that part of the function is below the x-axis, and let's see why. So let's take this area here. So f of x is this value here, and g of x is this negative value here. So if I take this positive value and I subtract this negative value, the net effect is that minus a negative is a positive. So what we're going to get is we're going to get this height of this rectangle as this plus this. And so that's how the integral actually takes care of these positive and negative issues for us. So this is remarkably easy and remarkably comfortable. If you really want to take a look at this a little bit more, here's a proof of this. What happens is that the differences cancel out here. Okay, so now what we need to do is we need to take a look at an example problem. So I have an example problem here where I want to find the area between 1 over cosine squared x and sine of x. All right, and here's 1 over cosine x squared x. It's written here as secant squared x, but that's an alternate form that you don't have to know. We will just keep it as 1 over cosine x. And so we're going to find the area between 0 and pi over 4. So we set up our integral as the upper curve minus the lower curve, and then we set our boundaries from 0 to pi over 4. We integrate one piece at a time. The integral of this, as you might recall, is tangent of x. The integral of negative sine x is positive cosine x. And so what we're going to do is we're going to substitute pi over 4 into both of these x's and get a number. And then we're going to subtract the number we get from by substituting 0 in. And if you do that successfully, you get pi over 2, root 2 over 2 units squared. Okay, and so what are some variations of this application? Because this is pretty straightforward. One variation is that you might not be given boundaries. It might just be find the area of the region enclosed by these two curves, but it doesn't give you from what point to what point. So what you have to do is you have to evaluate where those 2 points meet. So you can do this with your graphing calculator. You can do this algebraically, where you solve one function equaling the other function, and we find that we have these two x values. So that gives us our boundaries. So we simply do the upper function minus the lower function from those two boundaries, and we can do this algebraically. So again, we find the antiderivative of this and the antiderivative of this, or we can actually simplify this expression as they have done here, and then just find the antiderivative of this. Okay, which is this. Now we substitute the 2 in for both of these x's, and we get this. We substitute -2 in for both of these x's, and we get this. And we find the difference, okay, because when we evaluate a definite integral, it's the upper minus the lower. Okay, so we have the difference between those two, and we get something like 10 2/3. All right, and of course you can also evaluate it in your calculator by putting in this syntax. Okay, so you should be able to do that. So that's one twist, where they don't give you the two bounds, and so you have to find where they intersect. Another one is that, well, what if we want to know total area, which means that we don't consider the area below the x-axis as positive, as negative. What if we want to consider this as positive? So we've got this as positive, and we want to add this as a positive area. How would we do that? Well, we could do it two ways. One, we can think of this as two integrals. What we'll do is integrate from -3 to 0, and of course that'll be some positive number. And then what we'll do is we will find the area of this part from 0 to 1, which will come out to be negative. And so to balance that out, we'll subtract this negative number. So in effect, what we're going to do, so here's our first area here, which is going to be positive, minus here's our second area, the area over here, which is going to be a negative number, but we have a minus the negative number. That's going to change this area into a positive. So the bottom line is, what we do is we find this positive area and we subtract this negative area to make the whole thing positive. So this is positive and this is positive, and then we get this total area. The other way that we can do this is we can create a new function where we have the absolute value of this function here, the modulus, as the IB likes to say. If we find the modulus of this function and integrate that, then we don't have to worry about breaking it up into two different areas, and we can just go from -3 to 1. Okay, and those are all the tricks that you need to know of how to find the area between two curves. It's very straightforward, and I hope you find it to be very intuitive. As long as you see the big picture of what's going on between the two areas, I think you can manipulate the integrals to suit your needs, however you think that they need to be done. All right.